We're all using AI every single day, right? Whether you're asking a chatbot a question, making an image, or just talking to a smart assistant. But behind that smooth digital interface, there's a world of physical hardware. Servers, data centers, all of it using very real energy. So today, we're asking a pretty fundamental question. What is the real cost of all this artificial intelligence to our planet?
So let's just get right down to it. That one simple action. You type a prompt, you hit send, and you get an answer. How much energy did that little exchange actually use? It sounds like it should have a simple answer, but as you're about to see, it's a real rabbit hole.
For the longest time, whenever people talked about AI and energy, the focus was all on training. That gigantic one-off energy burn it takes to create a big AI model from scratch. But that conversation has totally shifted. Now it's all about inference. That's the little sip of energy used every single time you or I or anyone else actually uses the AI. And while the cost for one query is tiny, we're now doing it billions of times a day. It adds up so fast that it can completely dwarf the original training cost in just a few months.
Okay, so here's how we're going to break this all down. First, we'll look at the numbers people are throwing around for a query's cost. Then, we'll get into the measurement maze to see why those numbers are so confusing. After that, we'll explore the industry's incredible efficiency revolution, but then complicate things with the rebound problem. And finally, we'll try to figure out what this all means for our AI energy future.
All right, so what's the magic number? What's the cost? Well, if you go looking for a simple, straightforward answer, good luck. Because the numbers being reported by the big AI labs are, and I'm putting this mildly, they're all over the map.
So take a look at this. Google says a typical Gemini prompt is about 0.24 watt-hours. OpenAI is kind of in the same ballpark at 0.34. Okay, seems consistent. But then you see Mistral's assessment and whoa, it's somewhere between 3 and 42 watt-hours. How on earth can the numbers for basically the same kind of task be so wildly different? Well, it turns out it's all about what you decide to count.
And that confusion right there is why we need to talk about the measurement maze. To make any sense of these numbers, you have to know how they were measured. Because without that context, we're not just comparing apples and oranges. We're comparing, like, apples and engine blocks.
Okay, this is probably the single most important concept we're going to talk about today, the measurement boundary. It's basically the line you draw around what you're including in your calculation. Are you only counting the electricity going directly to the AI chip? Or are you also counting the rest of the server, the massive cooling systems for the whole data center, and maybe even the power being used by machines that are just sitting idle, waiting for the next query? What you include and what you leave out can change the final number by a factor of 10 or even more.
So let's take Google's approach as an example of a really comprehensive boundary. They don't just count the energy for the AI chip itself. They also add in the energy for the host computer it's running on, the power being drawn by idle machines kept on standby, and all that data center overhead, the cooling, the power conversion, all that stuff. This invisible infrastructure can easily double the energy cost compared to just looking at the active chip alone.
Now, while all this measurement stuff is super complicated, the tech industry has this really powerful counter-narrative, and it's all about the fact that they are making this technology more efficient at a pace that is just revolutionary. You have to remember, these companies are in an all-out war to make AI cheaper and faster. Energy is a huge part of that cost, so the incentive to get more efficient isn't just about being green, it's about winning. And the results of this race, honestly, they are wild. Get this, 44 times. That's how much Google says they cut the carbon footprint of a typical Gemini prompt. And that wasn't over a decade or something. That wasn't just 12 months. That's not an improvement. It's a jaw-dropping leap forward.
So how on earth did they do that? Well, it wasn't one single silver bullet. It was a ton of smart engineering all happening at once. They're using cleverer model designs like mixture of experts, which only fire up the part of the AI brain they need for your specific question. They're getting way better at packing queries together to keep the machines busy. And of course, on top of all the software tricks, they're buying up massive amounts of clean energy.
So, great. Problem solved, right? Engineering saves the day. Well, not so fast, because all this incredible progress is about to collide with a huge complication, often called the rebound problem. So the first challenge is what you might call the reasoning model wildcard. See, even as we're making simple AI tasks incredibly cheap, we're inventing entirely new, more complex types of AI. These are next-gen models designed to do long chains of, well, thinking before they give you an answer. And all that extra thought costs a lot of extra energy.
Just look at these numbers.
A typical query on a regular model might be around zero point 0.3 watt-hours, but give a long, complicated prompt to one of these new reasoning models, the energy use just skyrockets to over 33 watt-hours. That's more than a 70-fold increase for a single, more demanding query.
And it's not just about the model, it's about the task itself. This chart says it all, really. Asking an AI to just classify a piece of text is one thing, but asking it to generate a brand new image, that can be orders of magnitude more intensive. We're talking over 1,000 times more energy in some cases. Suddenly, the whole idea of an average cost per query starts to feel almost meaningless when the range is that huge.
The second big challenge is a classic idea from economics called the Jevons paradox. It's a fascinating concept. It basically says that when a resource gets way more efficient and cheaper to use, our demand for it doesn't just stay the same. It often explodes. If AI queries become practically free, we won't just use them like we do now, we'll build them into everything. And that could drive the total energy consumption way up, potentially wiping out all those incredible efficiency savings.
So where does that leave us? We've got these two massive forces pushing in opposite directions. Radical efficiency on one side and the potential for exploding demand on the other. How should we even think about this? Well, it might all come down to focusing on the right metric. This quote really hits the nail on the head. If we only focus on the efficiency of each individual query, it's like celebrating a car's amazing gas mileage while completely ignoring the fact that we're now driving it 10 times as much. To get a real picture of AI's impact, we have to look past the per query number and measure the one thing that truly matters, the total amount of energy being consumed.
But getting that total picture is incredibly difficult right now because there is so much critical information we just don't have. The major companies don't tell us their total query numbers. We have almost zero official data on the cost of generating images or video. We don't know the real-world mix of cheap versus expensive queries. And most of these claims we've talked about, they haven't been independently verified. Transparency is a huge issue here.
Which leaves us with this final, critical question. The efficiency gains are real, and they are absolutely spectacular. But the risk of the Jevons paradox, of demand exploding to consume all those savings and then some, is just as real. The future environmental footprint of AI is going to be decided by which of these two powerful forces ends up winning.